So there, as Hamlet says, there are more things in heaven and earth than are dreamt of in our philosophy, right? Hamlet to Horatio. And so there are a lot more vector spaces in heaven and earth than are dreamt of in the xy plane. There are a lot more situations out there where we can perform linear combinations. In other words, where we have closure under addition and closure under scalar multiplication and the existence of a zero vector and all those wonderful things. And there are a few examples that we like picking on pretty frequently, that the author of our book likes picking on fairly frequently. So let's talk about them real quick. One example is a set called P sub n. And this is the set of polynomials of degree maximum n. Polynomials of degree less than or equal to n. And the elements of this, let's just pick on one example. Let's take P2. So these would be polynomials whose degree is less than or equal to 2. Well, what do those look like? First of all, they're all functions, f of t. And because each one is a polynomial function that's built out of powers of t, so I might have a constant term, I might have a term that is a multiple of t, and I might have a term that's a multiple of t squared. And those multiples can be any real number that we like. So this is what the set P2 looks like. It's a set of polynomial functions, or if you like, polynomial expressions. It doesn't really matter whether we think of them as expressions or functions at this point. And the three sort of degrees of freedom, if you like, are what are the values of these coefficients, a, b, and c. So when we talk in a day or two about coordinates and basis elements and that kind of stuff, the a, b, and c we're going to think of as being our coordinates, and the things that they are multiplying, the building blocks, if you like, of the elements of our set, we're going to think of those as forming a basis. So we're not really rigorously defining what that means today, but I figured I'd mention it now so that we recognize it when we see it in a day or two. That the basis of a vector space is kind of our set of building blocks. And then the coordinates are the way that we build an element from those building blocks. They're the coefficients of a linear combination. The coefficients of a linear combination of these elements. Of the basis elements. So that's when we talk about coordinates and basis over the course of the next week or two. That's what we're talking about. The basis are the elements that we build our vector space out of, and the coordinates are how much of each one that we use to describe an element. So an example of a polynomial in this set might be, let's call it f1. I don't know, 1 minus 3t squared. That belongs to P2. And then we might take another polynomial, f2. 3 plus t squared also belongs to P2. So because this is not an example of a vector space which is just like R2 or R3 or something, it's a valid question to ask, what exactly do addition and scalar multiplication mean in this set? So what would it mean, for example, to add these two polynomials together? What would f1 plus f2 look like? How do you add two polynomial expressions together? Just add the terms, just combine the like terms together. So the 1 and the 3 are going to combine to give me a 4. The t from the second one is by itself, and so we'll just keep it. And then negative 3t squared plus t squared, negative 2t squared. And then again, whenever I add, crucially, whenever I add two polynomials whose maximum degree is 2 to one another, the result is also a polynomial whose maximum degree is 2. In other words, this set is closed under the addition that we just described. when I add two quadratic or lower polynomials together, I get a result, a sum, which is also quadratic or lower. So that helps us to see why this set is closed under addition. And it's also closed under scalar multiplication, because what would I get, for example, by multiplying f1 by negative 4? Again, we have the usual distributive property in algebra that does that for us. And that just says, let's multiply each one of these terms by 4 and get negative 4 rather, and get negative 4 plus 12t squared. But then again, that belongs to P2. Anytime I multiply a quadratic or lower polynomial by a constant, a scalar, I'm going to get another quadratic or lower polynomial. And it doesn't take too much to convince yourself that all the other fiddly properties of a vector space that justify what addition means and what scalar multiplication means and how they interact with one another, that those are all satisfied as well. So this P2 really is a vector space. Notably, and this is another thing that we can't really discuss on firm foundation until we talk about coordinates and bases. But we can sort of do it half-heartedly for a moment. How many degrees of freedom are there in my polynomial? In other words, how many coordinates does it take to single out an element of this set? I had the coordinates listed a moment ago. How many of them were there? 3.
How many coordinates does it take to what?
How many coordinates does it take to uniquely single out an element of this vector space? So if I'm playing a guessing game with you and I'm thinking of an element of P2, how many different numbers are you going to have to come up with in order to make a guess that's exactly right? Well, we need to come up with 3. There are 3 coordinates, and we called them A, B, and C a moment ago. Ultimately, this is going to be the same thing as how many elements there are in our basis. How many building blocks? How many basis elements? Is also 3. And this number is an important invariant property of our vector space called its dimension. So the dimension of a vector space is the number of coordinates that it takes, or equivalently, the number of basis elements that it takes, to describe each element in this vector space in a unique way, in one and only one way.
So the dimension is them combined.
The dimension is, well, it's either one. It's either the number of coordinates or the number of basis elements. Those two have to be the same. They must be the same. We'll see why when we define precisely what a basis is. But in fact, it's linear independence that's going to guarantee that this number is the same for both of them. So there's one example of a vector space that's not just the xy plane or xyz space or something, but because it is a vector space of dimension 3, it turns out, and this is the great miracle of linear algebra, that when we strip all the context away from it and forget that we're talking about polynomials and just descend to the level of using column vectors to represent everything, then we might as well be talking about R3 again. And we can use the tools of matrix algebra and all that stuff that we have from before will work the same way with these polynomials that they would with just points xyz inside xyz space. So there's one example of a vector space that's, I don't know, let's say non-standard. And so there are things that we might like to do with this vector space. There are things that linear algebra can tell us about this vector space. I mean, we've already sort of hinted that linear algebra can tell us the dimension of this vector space. But then, equally well, we can also, so let's take P2 again. P2 is the set of all polynomials of the form a plus b times t plus c times t squared. I can define now linear transformations on this vector space. So here's an example. We talked actually, when we first started talking about vector spaces as being more than just the xy plane, we talked about the derivative in calculus being a linear transformation. Let's not go there just yet. You'll have a chance to go there on your activity after the break. But here's an example of a linear transformation. I'm going to call it T. And this linear transformation takes an element of P2, so it takes a polynomial of degree maximum 2, and it produces for us a real number. So the domain of this transformation is the set of polynomials of degree maximum 2, and the codomain, what this transformation is going to produce, is a real number. And here's how I'm going to define this transformation. That I'm going to take a polynomial from P2, and I'm just going to evaluate that polynomial at 0. So it's a completely valid question at the moment. Is this really a linear transformation or not? To answer that, let's just get some practice applying this linear transformation and see exactly what it does. So let's suppose I take an element from P2, like the example we had before, 1 minus 2t squared. What's going to happen if I apply my linear transformation to that polynomial? What am I going to get? 1, because I'm going to get 1 minus 2 times 0 squared. So this polynomial, 1 minus 2t squared, gets sent to 1. If we take my other polynomial from the previous slide, which you're going to have to help me remember because I erased it, what was it? 3 plus t squared, thank you. So I take my other polynomial from the previous slide. I apply t to it. What am I going to get here? 3 plus 0 squared. It's going to give me 3. Now, if this really is a linear transformation, then it shouldn't matter if I decide to add my two vectors together, in other words, my two polynomials together, and then apply t. So the sum of these two was 4 plus t minus t squared. If I apply t to that sum, first of all, what do I get when I apply t to that sum? 4. 4 plus 0 squared. But on the other hand, what would I have gotten by, instead of adding the polynomials, instead I add their images under t? The same thing, exactly. 1 plus 3 coming down this side also gives me 4. And that lends some credence to the contention that this is a linear transformation. Because if it really is a linear transformation, we have to have that t of f plus g is equal to t of f plus t of g for all polynomials f and g. And then likewise for scalar multiplication. But it's not too challenging, I think, to convince yourself that that does hold. So this is actually a linear transformation. But because this is a linear transformation, so now here's the next place I want to push this, is that anywhere we have a linear transformation, we have a matrix. And anywhere we have a matrix, we have questions that we can answer using a matrix. And one of those questions might be, so let me cut this. Here's a question. First of all, what matrix can we use to represent T? Well, thinking back to 2 weeks ago now, how do we build a matrix that represents a linear transformation? Let's call our matrix A. What do we have to find? How do we do it before?
Just look at what D does the basis on.
Right, we just need to know what does T do to the basis elements. And so we have to say what are the basis elements of our vector space P2. So this is why we're going to start talking more and more about basis as we go along, is that when we first talked about how to build a matrix for a linear transformation, we first talked about it in the following context. I'm going to switch screens here real quick. When we first talked about building a matrix to represent a linear transformation, we said that the columns of that matrix, we called it a standard matrix when we talked about it before. The columns of the matrix were exactly the images of the standard basis vectors 1, 0. So this was T applied to 1, 0. And the second column was the image of the vector 0, 1. T of 0, 1. And because in this example 1, 0 is being sent to negative 1, 1, and 0, 1 is being sent to 5, 6, that's what told us the two columns that make up this standard matrix. But again, this whole process was dependent upon us having chosen in the domain those two vectors as our basis. So those basis vectors told us what to use in building this matrix. And because those basis vectors are what we call the standard basis vectors, this matrix is what we call the standard matrix. And so 1, 0 and 0, 1 are friendly standard basis vectors for the xy plane. But we have something different than the xy plane, and so we have a little more work to do to specify what exactly are the basis vectors that we're hoping to transform. Because what matrix we get depends on what choice we make. And a moment ago we were saying that the basis that we're thinking of, the building blocks for this space P2, are the functions 1, t, and t squared. And if that's the case, if we use those as our basis vectors, then the columns of my matrix are going to be the images under our linear transformation of those elements. So now to find my columns, I'm just going to transform 1 using t. I'm going to transform t, and I'm going to transform t squared. And again, the reminder, I erased this, I didn't mean to. T of f is f evaluated at 0. So tell me, when I evaluate the function f of t equals 1 at the point 0, what do I get? So if f of t is equal to 1, then what is t of f? If I put t equals 0 into that function, what do I get out? That's one that will break your brain if you think about it too hard. Because it's a constant function, it doesn't matter what t I put into my function f, I get 1 out, always. So when I apply our transformation to that function, which puts 0 in for t, I get 1 out of it. So moving on to the second column. If now I take the function f of t equals t, and I put a 0 in for t, what do I get out this time? If f of t is t, then what is f of 0? 0. I'm putting a 0 in for t. So the second column of my matrix is 0. And finally, for the third column, f of t equals t squared. So when I put a 0 in for t, I get 0. There we go. And so there's a matrix that represents this linear transformation with respect to the basis that we chose. So it's getting more clear how choosing a basis is going to affect your matrix, because it tells you what are we transforming to get those columns. So there's our matrix 1, 0, 0.
Shouldn't this be a 3 by 3?
Let's do a quick example of how this matrix can stand in for a linear transformation. Suppose now that I'd like to know what is t applied to the polynomial negative 4 plus pi times t minus the square root of 2t squared. Well, how do I make this matrix stand in for that linear transformation? Well, I'm going to take my matrix, 1, 0, and 0, and then I'm going to multiply that matrix by a column vector which has the coordinates of this element, negative 4 plus pi t minus square root of 2t squared, with respect to the basis 1t t squared. And the coordinates are negative 4, pi, negative square root of 2. Now, how do I multiply that matrix by that vector? Negative 4 times 1 plus 0 times pi plus 0 times negative square root of 2. There's actually only one entry in this product, because again we're multiplying across this row, down this column, and adding the results. And so I end up getting negative 4. Which, by the way, is exactly in coordinates, sorry, in our coordinates on the real line, this would just be the number negative 4. That's exactly what we would have gotten by evaluating this function at 0. So anything we do with a linear transformation, once we have a matrix for it, we can do the same thing with that matrix. Once we have taken the context of the entries in our vector space, once we've taken the context away and just boiled it down to coordinates instead, then the matrix multiplied by the coordinate vector does the same work as the transformation applied to our element of P2.